Hi there, I'm Jocelyn Barbosa, and in this video we are gonna learn linear regression, which is considered to be one of the simplest machine learning algorithm used nowadays that has a model or statistical model that shows the relationship or correlation between two variables. So what is linear regression? For us to have a good grasp or understanding on what linear regression is and how does it work, let's try to take a look at the linear regression algorithm. Looking at this graph, we have the x-axis that represents the independent variable and the y-axis that represents the dependent variable. When we say dependent variable, it's a target or response variable that is continuous, whose value is to be predicted, while independent variable is a predictor variable used to predict the target or response variable y, as we can see here. So if we have a sample data or a value of x that is the independent variable, say we have the value of x here or increasing value of x and the y values, and that when y increases as x increases, you'll get a value or a positive regression line over here, as we can see here. In contrast, when we have a value of x, increasing value of x, however the value of y decreases, then we can have a negative regression line, or the slope of the line is negative. Say we have a data here, observable or observations, number of observations or instances, and we scatter plot them, and our task is to find the regression line or to create a best fit line. And once the regression line is created, we can now predict or do the prediction. Let's say we have the estimated value here or the predicted value as well as the actual value. The goal here is to reduce the error, or that is to reduce the distance between the actual value and the estimated or the predicted value. Suppose, and that is of course to minimize the error. Also, suppose we have a graph here, speed in the x-axis and the distance covered in the y-axis with a fixed time duration. And if we plot a graph between the speed traveled by a car or a vehicle and the distance traveled in a fixed time duration, then we can get a positive regression line or a positive relationship between these two variables. Here, y is our distance traveled in the fixed distance duration, and x is our independent variable, the speed of a vehicle. This is the slope of a line, the positive slope of the line, and here is our y-intercept of a line. So that means that there is a positive correlation between the speed of a vehicle and the distance traveled in a fixed time duration. That is, increasing the speed would also increase the distance traveled by a particular vehicle. So here is another example of a linear regression and how linear regression algorithm works. We have the independent variable and the dependent variable. So say we have 1, 2, 3, 4 and 5 values of our independent variable x, and so with y, and if we are to scatter plot them, we have here, if the value of x is 1, y is equal to 3, 2, y is 4, and if it's 3, y is 2, if it's 4, y is 4, and 5, y is 5. So granting we have this, and we are to, for us to get the regression line, we are to follow the previous regression formula, that is y is equal to mx plus b, and for us to get the slope or the regression line, we are to get, or the mean of this, x, which is 3, the mean of y here is 3.6. We have the slope, or we can get this regression line based on this data, that is following this equation, y is equal to mx plus c. So how do we get the slope or m? We have the summation of x minus x prime, or mean x, y minus mean y, over the summation of the square of the difference between the mean x. So if we are to calculate the difference between the value of x and the mean x, we have here, if this is our mean x, or the average x here is 3, and we are to get x minus x mean, we have 1. If the value, if x is 1, then 1 minus 3 is negative 2. then 2 minus 3 is negative 1. Then if the value of x is 3 minus 3, that is 0. 4 minus 3 is 1, and 5 minus 3 is 2. That is looking at the distance between the value of x to the mean x. Similarly, for the y-axis, we have the y value minus the mean y. For example, if the value of y is 3, then we have 3 minus 3.6. That is the average y over here. 3 minus 3.6 is negative 0.6. 4 minus 3.6 is 0.4. 2 minus 3.6 is negative 1.6. 4 minus 3.6 is 0.4, and 5 minus 3.6 is 1.4. And then what we are lacking right now is the square of the difference between this x and the x mean, or the mean x. And so if we are to calculate, we have square of negative 2 is 4, square of negative 1 is 1, 0 for 0, and then 1 square here. 1 square is 1, and 2 square is equal to 4. So having calculated or computed all of these values here, we can now get our slope by multiplying first these two guys here. We have negative 2 times negative 0.6, and that is 1.2. And then negative 0.4 here. 0 times 0 is 0. 1 times 0.4 is 0.4. And then 2 times 1.4 is 2.8. And getting the summation of all of this, we have 4 for these values here. And the sum of these values over here is 10. And so our slope is 4 over 10, or 0.4. And so we have this equation, y is equal to 0.4x plus c. But how do we get c here? If we try to take a look at this, we have y is equal to mx plus 3. Substituting the value of our y here, which is the mean y, that's 3.6, and the mean x is 3. So we have 0.4 times 3 plus c, and so we can actually solve c is equal, or come up with the value of c, that is 2.4. And as such, we have y is equal to 0.4x plus 2.4, where c is our y-intercept, somewhere here where our slope, or our regression line, intercepts the y-axis. Here is our intersection between the mean x and the mean y, where our regression line touches the y-axis also. Okay, so now that we have already came up with this equation, y is equal to 0.4x and 2.4, we can now predict y for x is equal to 1, 2, 3, 4, and 5. And substituting the values here, we can have at x is equal to 1, the value of our predicted value of y is 2.8 here. And if the value of x is 2, then our y is 3.2. And if it's 3, the value of y is equal to 3.6. And if the value of x is 4, then we have 4.0, and then finally we have 4.4. In the line passing through all these points, or these predicting points in cutting via y-axis at 2.4, which is our y-intercept, is the line of regression. So this is our slope, and following the equation, y is equal to mx plus c. And our task now is to calculate the distance between the actual value and the predicted value. And our job also is to reduce the distance, or reduce the error between the actual and the predicted value. And then the line with the least error will be the line of regression, or regression line, or what we call the best fit line. Okay, so let's now check how the model performs. And to do that, we have a method called the R-squared, wherein this is a value. R-squared value is a statistical measure of how close the data are to the fitted regression line. It is also known as a coefficient of determination, or the coefficient of multiple determination. So to do that, we try to substitute here the values of our y and the predicted value y and the actual values of y. So first we get the mean value of y, that is 3.6, or our y prime, and looking at the actual versus the predicted value, we use this formula: r squared is equal to the summation of the predicted value y minus y prime square over the summation of y minus the mean y, or y prime square. So we do the substitution. We try to calculate first the denominator of our r squared. We have here y minus y prime, that is, our y is 3 minus 3.6, this is negative 0.6, and we have 4 minus 3.6, or 0.4, negative 1.6 for 2, and then 0.4 for y is equal to 4, and for y is equal to 5, we have 1.4 over here. And so we get the square of these values here, and these are the corresponding square value of this y minus y prime. And to solve for this numerator of our r squared, we get the predicted value, that is, at x is equal to 1, the predicted value is 2.8, as we have plotted earlier, 3.2, and so on and so forth. And so we get the distance between this predicted value to the mean value of our y. This is actually our mean, that is 3.6. That is getting the distance from this yp, that is 2.8, this guy here, minus the y prime, or the average, or the mean that we can get, that is 2.8 minus 3.6, that is 2.8 minus 3.6, we have negative 0.8, 3.2 minus 3.6, that is 3.2 minus 3.6 is negative 0.4, 3.6 here as our predicted value, minus our mean value of y, that's 3.6, so we get 0 over here. Then 4 minus 3.6 is 0.4, 4.4 minus 3.6, which is the mean value of y, we have 0.8. And then we have to get the square of these results here. We have 0.64, 0.16, and so on and so forth. And so we can now calculate the summation of these values here. We have 1.6, and for y minus y prime squared, we have 5.2. Substituting the values, we have 1.6 over 5.2. Then we have a value which is approximately equal to 0.3. This means that if the value of I squared is a little bit smaller, then that means that there is a sparsity of our data points. This means that if this suggests that the data points are far from the regression that we have created, and perhaps that's because of the input data points that we have considered earlier as our independent variables. And if there is an increase of our r squared that is approximately equal to 0.7, then there is also a significant difference as to the data points being not so far from the regression line. And might as well, if the value of r squared is somehow estimated as 1.0, then that actually increases the performance of our regression line. So, but at this point, our value, based on our regression line that we have came up, our r squared is estimated as 0.3. Okay, so linear regression is actually a method to predict or target or dependent variable y based on the values of the predictors or independent variable x. Please take note that when we talk about dependent variable, it is just the same when we say target variable or response variable. As we have been emphasizing before, LR, or the linear regression, can be used in predicting a discrete continuous quantity. So for example, looking at the use case of the linear regression, if we have observations or data here with y-axis representing the dependent variable or response variable, which is for example the house size, and we have the dependent variable in the y-axis, what would be the price of a house given a particular size. And so with this, we fit a line to it. And from the fitted line, we could do a lot of things. One, we can compute the r-squared if that would determine if the house size and price are correlated, or has it a positive correlation or a negative correlation. But in this case, in our example, there is a positive correlation between the house size and the price, and then the large values imply a large effect. And we can also use the line to predict house price given its size. Then the price of the house can be predicted with this value. And if there is somehow the size is smaller, then the price is also a little bit lower. That means there is a positive correlation between the size and the price. As the size increases, it shows that the price also increases. Okay, so looking at the mathematical equation of the linear regression, this is based on what we have mentioned earlier, the y is equal to mx plus b. Here we use b0 as our y-intercept, and b1 is our slope, that is, we use m earlier, and e is the amount of error. Okay, just a summary, we have here the target response or the dependent variable y and our independent variable x, and here is our y-intercept, and this is our slope and the error that we can find while doing the fine-tuning and coming up with the regression model. Okay, so as we can see, this is a few of the examples of the use case of a linear regression. And there are also sometimes or cases like we have more than one independent variables. For example, you don't only consider the house size but also consider the number of bedrooms, for example, that might have an effect to the price. Okay, so another use case where linear regression model is being used, for example, to forecast the sales by looking at the relationship between the annual sales and the advertising cost. So if we plot this in our graph, and this is using the MATLAB, but we can also make use of another tool like Python, for example. And then here we can say that there is a positive correlation between the advertising cost and the annual sales. That means that the data is telling us, the graph is telling us that if as the advertising cost increases, the annual sales also increases. Here is 850, and if we increase it to almost 35, that is in million euro, then there is also an increase in annual sales, and so on and so forth. So this is how the linear regression model is being applied. Another example is to forecast the price of the house by looking at the relationship between the house price and the size of the house, as we have mentioned earlier, but somehow this is a little bit realistic. That is based on the statistics of managers using Microsoft. We can come up with a regression line like this. So somehow there is also a positive correlation. And also to forecast the fatal traffic accidents by looking at the relationship between the accidents and the population of the states. So let's take a look at the graph. And also it's telling us that as the population increases, there is a high likelihood that the number of accidents also increases. So okay, just to summarize the characteristics of a linear regression, that is in terms of these bases or the aspects or components that we have looked into and the corresponding description. We have one, the definition. Yeah, we have already defined it earlier. Like linear regression is a model to predict target or dependent variable y based on the values of the predictors or independent variable x. What type of variable used? That's continuous dependent variable, as you can see early in our previous demonstration. The estimation method, we have least square estimation. Selecting the line with the least error will be the line of linear regression or regression line, or the best fit line. And what about the concept on data modeling? So the data is modeled using the straight line, and this is our mathematical equation for the linear regression, with the y-intercept over here and the slope of the line, and we have the independent variable, we have the dependent variable y. And what about the relationship between dependent and independent variables? So with linear regression, it has a linear relationship between dependent and independent variable. Either we have the positive correlation or the negative correlation, where the slope is negative. And for the output, the predicted value of a variable, of course, the continuous value or quantity. What about the performance measure or goodness of fit of the line? So it's measured by the loss, as we have shown earlier, the r squared, wherein if the value of the r squared is a little bit smaller, then there is an implication of the distance of from the detected or from the predicted y value to the actual value. And on the applications, this can be applied as based on the use case that we have shown earlier in forecasting sales, business domain, and also in determining risk in financial services and insurance domain. So, okay, that's all for linear regression, and I'll see you in the next video.